Hello everyone, what I want to do in this video is look at two interesting problems from the prelim spring 2019, really June 2019. And those problems are 2 and 3. So I particularly want to look at 2. This is a really interesting problem. It investigates when the composition of a monotone function and a measurable function is measurable. And it also looks at whether you can take the composition of whether exists a non-measurable function f where the composition of g and f is measurable, where g is monotone. Okay. So yeah, I'll do 2 here. And 2 relies on some stuff from 511. Or at least stuff we could have done 511. I don't know if you did, probably not. So one thing you definitely did, and this is even taken from the Bartle and Sherbert book, and that's the characterization theorem of intervals. So if S is a subset of R that contains at least 2 points and has this property where x, y, and S for x less than y implies this interval x to y is an S, then S is an interval. And by an interval, we mean simply a closed, half open, half closed, open interval. It could be infinite, could be finite, but it's interval in the usual way.
All right, so to prove or to solve this problem, I need a little proposition that really is basically 511 type stuff. So let's assume that G is monotone on R. And the problem is not specifying whether G is real valued or not. So let's assume it's extended real valued. That. Okay, so the claim is either this inverse image for any C positive, and we could do this for other inverse images. Let's just look at this. Why not? We're ultimately trying to prove that G composed with F is measurable. So either this is empty or this is an interval. So let's give this a name. Let's call this S. So either S is empty or S is an interval. Right. All right, so the proof is pretty easy. We're going to use what we just had up in a second. So assume S is not empty. All right, so S is not empty, so pick something in it. So first, let's first assume G is increasing. The decreasing case is not going to take a whole lot longer, so I'll just do it. Okay, so let's say we have, let's say we have some Y in S. So such a Y exists. Well, let's just assume X is less than Y. Well, G is increasing, so G of X is less than G of Y. Y is an S, so G of Y is less than C. So this is less than C, implies that X is an S. Okay? So in particular, S has at least 2 elements. Anything less than Y, if Y is an S, is itself going to be an S. Right? So, And basically the same argument says that if u is in x to y, yeah, so u is less than or equal to y. It's basically the same thing. Applies g of u less than or equal to g of y, less than c. And well, that implies the closed interval x comma y is an S. So we picked arbitrary x and S, y and S where x is less than y. I mean, we're being a little redundant because x less than y and y and S implies that x already is an S. But yeah, we know this has at least two elements. Pick any two elements, x and y and S, where x is less than y. Then the closed interval itself is an S, and therefore, and this implies S by what I just had up a minute ago, is so actually case 2 is almost the same. So I'll leave that for you to do. There you would start out with an arbitrary x and S and pick y bigger than x. So then g of y is less than or equal to g of x is less than or equal to c, because g is decreasing. And same thing here. Instead of comparing g of u to g of y, you would compare g of u to g of x. So yeah, basically, yeah, I could just, if erasing wasn't such a pain here, I would just erase a whole bunch of stuff. Okay, yeah, so let's get to the problem here. Now this is very easy. The solution to 2a. There, it's right here. So we're going to look at this composition. So so let's say C is positive. We need to show this is measurable. And that's very easy. All right, well, basically done. Why? Well, this here is empty or an interval. If it's empty, the inverse image of an empty set is empty. If it's an interval, the inverse image of an interval, sorry, the inverse image of the empty set is the empty set. So trivially measurable. Regardless of whether f is measurable or not. If this is an interval, then the inverse image of an interval is measurable because f is assumed to be measurable. And henceforth, either way, this is measurable. So this is measurable. For all c bigger than 0. And that implies that G composed of F is measurable on R. And that completes the proof of 2a.
Yeah, if you don't know the trick, then this is a tough problem. But if you know the trick, it's very easy. Okay, so what's 2b? For every continuous, not strictly monotone function g. Actually, this, we don't care about continuity. So as long as we have a, really, you don't even care about not strictly monotone. As long as, so basically for every g that is not injective on R, there exists a non-measurable function on R such that g composed with f is measurable. Okay. So if g is continuous, not strictly monotone, then is not injective. An injective monotone function is trivially strictly monotone. It's nothing to that. Okay, so yeah, assume, but I'll explain why the problem is stated like this. Assume there exists A less than B. So I'm just literally saying what it means to be not injective. Okay. Okay, so now pick any non-measurable E. I don't care what, just any. So we need to cook up a non-measurable function, and you don't have to really go far and wide to do that. Let's say this is A times characteristic function of E plus B times the characteristic function of the complement of E. Okay. Verbs are nice. Sound like a caveman otherwise. F not measurable. F is not measurable. The easiest way to do this is, well, we know if F is measurable, the inverse image of singletons is measurable. Well, this equals E. It is not measurable. So yeah, we're done with that. There's really very little to do. Okay, and why is a composition measurable? Well, that's very easy. So again, the point I'm trying to make is cooking up this F is easy, but it's, if you didn't think to do it, it's tricky. That's why I'm making a video on this. Yeah, so right. So I claim this composition. Well, the simple reason is this is simply a constant on R. Constants are trivially measurable on the whole real line, on any measurable set. Well, if X, let's see why. If X is an E, then G of F of X. F of X is A, because X is an E. So X is an E, so F of X is A. So this is G of A. But whatever. Okay. Well, if X is in the complement, the same thing, except, well, I see where this is going, maybe. So yeah, in this case, F of X, so X is not in E, so F of X is hello, I guess. F of X is B because X is not an E. So this is G of F. Sorry, G of B. Well, yeah, right. This is G of A. Well, X is either an E or it's not an E. Either way, G of X is G of A. for all, sorry, that makes no sense at all. G of f of x is g of f, g of a for all x in R. Okay? And hence it's measurable because it's a constant. Okay, now I want to do 3, and there's really not much to 3a. In particular, so what is 3a? F is measurable, G is bounded and continuous on R. Prove that G composed with F is integrable. Well, G is continuous, so G composed with F is measurable. That's easy. We've done that in the video and lecture. Because inverse image under G of open sets is open. So yeah, G composed with F is measurable. And also G composed with F is bounded because G is bounded. So the integral over 0 to 1 of G composed with F is certainly finite. So it's integrable. It's measurable. The integral of its absolute value over 0 to 1 is finite. So what's much more interesting, and I wouldn't say this is terribly deep, but it's interesting, is the following. For every continuous unbounded function g, there exists an integrable non-negative function f where g composed with f is not integrable. So yeah, this is, if you don't really know kind of the trick to doing this, this is definitely very hard. Or not so much hard, but you probably wouldn't think to do it the way I'm going to do it. And honestly, I forgot really how to do this, and I had to look it up just because I don't want to spend too much time thinking about this. And yeah, the only way we're actually only use of continuity here is going to be to ensure that G composed with F is measurable. Okay, so G composed with F is measurable. So the issue is, or to show it's non-integrable, we have to show that the integral from 0 to 1 of the absolute value is infinity. So let us do that. So we have a unbounded function G on 0 to 1. Right. 1 second. Okay, so for every non-negative integer n, pick x n in 0 to 1, where absolute value of g of xn, 2 to the n works, but 4 to the n is even more fun. Yeah. So let's do 4 to the n, but 2 to the n also works. I guess 4 to the n is a little clearer somewhat. Okay, so yeah, we're done with G and the and using its unboundedness. Now let's kind of very cleverly cook up F. So note that, and if you can come up with an easier way to cook up such an F, I'm all ears. So notice that these, sorry, I want the other way around. I want this closed, this open. For n equals 0 to infinity, partitions 0 to 1. Okay. So this is yeah, so like what is this? I'll write a few of these out. So why is it so basically what I'm saying is, n equals 0, we have 0, 1/2, disjoint union, n equals 1, 1/4 to 1/2, et cetera, et cetera. So it's 1/8, sorry, 1/4 to 1/8. This would be n equals 2. So trivially, this partition 0 to 1. All right, so let's define a function in a very simple way. Let's just say it's xn. So all I need to do is define f on each of these intervals because they partition 0 to 1. So on each of these intervals, define it to be xn. And I claim that's it. We're done. Okay. So I forget the term the book uses for such a function where it's not really a simple function because simple functions are finite linear combinations of characteristic functions. I think the book calls it a semi-simple function. So this is semi-simple. It takes on countable number of outputs on measurable sets, so it's measurable. You can see that in the following way. This is this infinite sum here, xn, and I'll accentuate this is a characteristic function. Almost looks like a hammer and sickle here, but well, whatever. So it's a characteristic function. And the point here is that this is the pointwise limit of simple functions. What are my simple functions? Well, just n equals 0 to big N of this right here. Looks a little better. Right. Obviously, it's not negative because each xn is between 0 and 1, and that trivially gives me integrability. This is less than or equal to 1 because, well, everything here, the outputs are xn's, and these xn's are between 0 and 1. So this is, right. This is less than or equal to 1. So, yeah, so f is non-negative, integrable. Let's prove that G composed with f is not integrable. Okay? Again, it's measurable, so we need to show that the integral from 0 to 1 of the absolute value is infinity. And it's going to be definitely infinity. And this is a nice little estimate. I don't know if we've done things like this in lecture. So finally, so the only reasonable thing to do is break this up in terms of these partition intervals. Because we know exactly what f is on each of these partition intervals. It's equal to xn on each one of these intervals. So this is going to be equal to I'll write it like this. So it's g of xn, so let's pull it out of the integral. So this is bigger than 4 to the n. And this is just the difference of these two. Which we'll see. I mean, you could take the difference. This is bigger than the sum here. 4 to the n. 2 to minus n minus 2 to minus n minus 1. Well, what is this? This, of course, is just equal to, this is a beautiful but trivial property of kind of playing around with partitions of the real line, where you would go from n equals minus infinity to infinity, or partitioning 0 to 1, going from n equals 0 to infinity. Using these kind of these numbers here, 2 to the minus n's. The difference here is basically 2 to the minus n, because it's 2 to the minus n minus 1/2 2 to the minus n. And that's just 1/2 2 to the minus n. Okay. So this equals, pull the 1/2 out. Well, it's 1/2 n equals 0 to infinity to the n. And that's certainly infinity. That's, 1 plus 2 plus 4 plus 8 plus 16, and so on, so on, so forth, times 1/2. So this is certainly not integrable. The integral is definitely infinite.